Hey everyone. I love the statistics and probability unit. As much fun as geometry is, and as tickled as my brain is by puzzle solving aspects of higher level work with equations and functions, at my heart, I'm a person who cares deeply about social studies. And those who know me as a teacher in the classroom know that I also coach debate clubs so that I can express that side of myself as a teacher, despite being assigned to math and science. I can't not talk about social studies. It's too important to all parts of our lives. The reason I love stats and probability so much is that this is where we see math's impact on social studies, and can use our learning about math to not be fooled by people when they're trying to lie to us through numbers. There are a lot of people out there who do that. Statistics can be a powerful force for understanding our world, when it's used properly. But it's also far too often used as a way to twist real information into something misleading. I believe that the statistics and probability unit, at its best, is training for students of social studies to be able to use those numbers for good in the work that they do, and see through when someone's trying to fool them. After all, and pardon me for swearing, but it's a quote, as first said by an unknown person but then made famous by Mark Twain, there are three kinds of lies: lies, damned lies, and statistics. Today, we're going to start our stats stuff with a few simple definitions and examples. We're going to start with the one that you've almost definitely heard of before, though maybe you don't see it called by this name so often. It's the mean, more commonly called the average. It's the average of a group of numbers. It's usually referenced more than the other two things we're going to talk about today, in part because it's very useful, but in another part because it's one of the most misleading ones in a lot of ways. Let's look at how it's useful first. The mean is just a complex form of division. You're taking things that are already divided, but unevenly, and looking at how much each group would have if they were split up evenly. Ideally, it's a way of ensuring fairness. A good example for this would be something like candy. Packages of candy are not all the same. Not every single bag of Skittles, for example, has the same number of candies in it. There's an element of randomness to that. The makers want to make sure that you're not feeling ripped off if you buy a bag, though, so they need to make sure that you don't get too few in a bag, and they also want to make sure that the bag doesn't have too many, because then they'd just be giving them away. So, they set a target average. If one bag of candy has 50 pieces in it, you're probably pretty happy with that. If another has 60, you're probably equally happy with that, because honestly, who counts their bag of Skittles to know if they have 50 or 60? You'd probably only really notice if you had way too few or a really high number. So, let's take a look at the data from 10 different bags of Skittles. Now, if I were to add all of these numbers together, in 10 bags of Skittles, I have 540 pieces of candy. That's a heck of a sugar rush, and I don't need it. So I can divide them back up into 10 equal parts and put them back into 10 bags. 540 Skittles actually fit perfectly into 10 bags as equal groups of 54. That means that even though only one of these bags actually had 54 candies in it, when I started, the mean, or average number of candies in all of the bags was always 54. And yes, I looked it up. 54 is the actual mean number of Skittles in each bag. So to review how we got it, we took a set of numbers, added them all up, and then divided that sum equally by all members of the set, so they all had the same amount. This tells me that if I buy a bag of Skittles every week for a year, by the end of that year, I'll have eaten an average of 54 Skittles a week, even though on one week I might eat 51 and on another I might eat 60. The mean is also very useful for biologists. A common way to figure out populations of wild animals, for example, is to take samples of their populations from a few randomly selected areas and use the average of those numbers to make an educated guess. If a marine biologist wanted to know how many clams live on a beach without actually counting every single clam, she would have to sample a few spots along the beach, count the clams in those, and then find the average number, the mean number, of clams per square meter that she counted. Once she knows how many clams are in the average square meter, she can multiply that number by how many square meters the whole beach is and get a pretty good guess. So why shouldn't I always trust the mean? Well, the mean works great for things that actually are spread mostly evenly across a population. Average heights and weights tell us how to design things to be most comfortable for most people. Average populations help us track animals. Average distribution and packaging helps us make sure that if you buy a pack of something, everyone who buys that pack gets about the same amount. But not everything's even. As a really quick example, I'm 32 years old at the time of filming this. My students are mostly 10. If I'm on a field trip with a group of 6 of them, our total age, the sum of all of our ages, is 92. 6 10-year-olds, 60, plus me, 32. If I divide that by the 7 of us again, our average age is just over 13, despite the fact that there isn't a single 13-year-old among us. An outlier, someone or something that's either really far above or really far below the average, can make the mean number a bit misleading. Check out these 2 pictures. In both cases, if I take the sum of all of the money of these people in these pictures and find the average amount of money for every person in both of these pictures is around $100,000. They're pretty different pictures though, right? In one of them, everyone actually has around $100,000. In the other, one super rich person makes the total of money a lot higher, and 9 broke people have none of it. But it would still be completely true if I said that both of these pictures show an average wealth of $100,000. This is one way that averages can be used to fool us. Politicians love to talk about the average wealth of people because we tend to imagine the first picture and we're happy about it. The dark side of that is that unfortunately, most of the time they're actually talking about the other picture. And when the numbers get even bigger, it gets even worse. Not to get too current eventsy, because I want this video to last, but it was just announced last week that the CEO of Amazon is on track to be worth $1 trillion. $1 trillion is a lot. That is a million millions. If one person has $1 trillion and also owns 999,999 slaves who make $0, on average, the mean amount of money for all of those people, they're all millionaires. If we just look at the average, this is great, but it's not, because the average isn't what's actually true. They don't all have $1 million, because one person has hoarded all that for themselves and left 999,999 people broke. So when the mean doesn't work, what can we turn to? Well, more instructive numbers might be the median or the mode. These are 2 different features that a set of data has. They're both fairly simple concepts, but they can be really useful in circumstances where the mean could either be misleading or just not useful. Sometimes it just doesn't matter. Let's start with the median. The median is the value that splits the highest half from the lowest half of our set. If we're talking about those 10 people where one makes $1 million and the others make less, the median would likely be a much more useful number. To find it, we put all of the data in order from least to greatest. Then we take the value that falls right in the middle of the scale. In this case, since we have an even number, we have 2 numbers in the middle, and need to find their average. If there were an odd number of values, there would just be one right in the middle, and we could just look at that one right away. Either way, our median number is going to be a lot closer to what most of the people in this group actually make. It's a useful number when you have one of those outliers that I mentioned before that would really throw the number off if you just took the mean. The mode is another thing that could be useful. That's the number that shows up the most. In my earlier example of the field trip group, we have 6 10-year-olds and 1 32-year-old. Since in our data set the age 10 shows up 6 times and 32 only shows up once, our mode, our most common number, is 10. The most common age in this group is 10. Even though there's an adult supervisor, it still probably makes more sense to say this is a group of 10-year-olds than to say this is a group with an average age of 13. And that's our 3. Remember, when you see statistics in news articles or hear them quoted to you, question the number you're hearing. Whether you're being told the mean, median, or mode can really change the story that your numbers are telling you. Are you really hearing the number that represents the facts, or are you hearing one that, though maybe mathematically accurate, could mislead you into believing something that isn't true? Numbers don't lie, but they also don't always tell the truth, and the way they're being used matters. The best way to make sure that you don't get tricked is to understand how they can be used and hold people to account if they're using numbers irresponsibly. We're all done here. Hope a lot of you are more comfortable with what these words mean. Peace.